Yes, so today I wish to tell you about, start a discussion regarding some aspects of the phenomenology of light scalar fields, their use in cosmology, and especially scenarios in which feeble coupling to matter is introduced, whether it be coupling to standard model matter or in radiation or to dark matter. So my perspective in this talk will be that there are at least three, let's call them phenomenological channels, relative to which new scalars are invoked. The first one is I will call the gravity channel or the minimal gravitational channel. The second one, with regards to invoking scalars as mediators of new forces, and then the last one regarding using scalars as dynamical drivers of variations of fundamental constants over cosmological and over cosmic space and time scales. And if I have sort of a message or a lesson, at least for myself, if not for you, is that while it is tempting to often want to zoom in and consider only one of these effects in our model building, the interplay between all three of these channels is inevitable and must often be taken into account. So this is a short talk. I'll briefly review those three phenomenological channels to invoking light massive scalars in cosmology, and I'll briefly touch on aspects of their interplay in some case studies and some of my work, and also work that I share with others. So the gravity angle, the minimal gravity angle, in other words, the use of misaligned scalars as dark matter candidates. So in this paradigm, the homogeneous mode of a new scalar field, along with small adiabatic fluctuations, is invoked as a potential dark matter candidate. This is the so-called ultralight bosonic dark matter paradigm, sometimes called wave dark matter, fuzzy dark matter, depending on the specific mass at play. Generally, we're talking about masses below an electron volt. In principle, when it was proposed, going all the way down to 10 to minus 20, I think the original proposal was for around 10 to minus 22, although that's going to be qualified. So such a scalar, minimally coupled to gravity, obeys a covariant Klein-Gordon type equation. And because it is a scalar, we can go to the cosmological mode, the zero mode, the k equals 0 spatially homogeneous mode, and just pick an initial condition there without violating any symmetry, because this is just a scalar. The equation of motion for that mode then simplifies greatly. The covariant mess just clears, and you reduce down to an equation that only depends on time. That maps on nicely to the equation of a damped harmonic oscillator, where the damping coefficient is played by the Hubble scale. And what is true of that equation, if you solve it with some initial condition, is that the energy density, so the field will start being frozen at early time, it stays fixed at the initial condition, and eventually starts oscillating. And then this so-called condensate then oscillates and contains an energy density that redshifts like that of non-relativistic dark matter. And this is often the expression that is used to relate the relative abundance to the dark matter density as a function of the mass of the field, here assumed to be greater than H equality, which is 10 to minus 28 eV, and the so-called misalignment angle, which is the dimensionless field, its initial condition. Now, redshifting like matter as a whole is a necessary but not sufficient condition to be a good dark matter candidate. One must look at what's happened on smaller scales. And indeed, on smaller scales, these field-type dark matters exhibit what's known as quantum pressure. It's essentially on physical scales that are smaller or of the order of the Compton and de Broglie wavelength, the waviness of the field is revealed. And that can correspond to large fluctuation in gravitational potentials in galactic systems, or cosmologically, this causes a suppression of cosmological structures, which are excluded, at least as, which leads to excluding these models as all of dark matter. So observations of ultra-faint dwarfs prevent this from being all of dark matter below 10 to minus 19 electron volts. Cosmology, the combination of CMB and galactic clustering, constrains anything below 10 to minus 24. Now, anything below the 10 to minus 28 will start behaving like matter, start oscillating after matter radiation equality. So this would have to be a subfraction of dark matter anyway, because it couldn't have been all of dark matter because it wasn't behaving like matter yet. And anything below 10 to the minus 33 is really more properly thought of as a dynamical cosmological constant. The second way new scalars are involved is sort of the so-called fifth force angle. So you might want to consider fifth forces in different setting. Maybe you're an n-body simulator, and you want to do an n-body simulation of astrophysical or galactic objects, and you're interested in introducing a new potential term in addition to the usual gravitational interaction between two bodies. Very popular parameterization is the following: the Yukawa type, where you introduce the prefactor is essentially the Newtonian 1 over r type potential. The lambda exponential cutoff allows you to introduce some short rangeness. And then, especially in a gravitational context, you might want to characterize the strength of the new force relative to gravity. So you introduce these coupling d, which d equals 1 would correspond to gravity, and d less than 1 would be less than gravity. You could also do that between this characterization between standard model particles if you are an experimentalist in the lab and do sensitive tests of fifth forces between spheres of material. Of course, this is a force law. This is often all that is needed, but if you don't believe in action at a distance, you would want to parameterize this, introduce a field that mediates this interaction. This is the age-old, classic physics problem of matter influencing field, field influencing matter. The equation for the field is Poisson-like in nature, where the right-hand side is the matter density weighted by this coefficient d, and then a length scale to account for the finiteness of the force. And then the equation of motion is simply Newton's second law in this case. And here I have suggestively, you can check that I've suggestively rewritten these equations by invoking this function, which I will suggest as a field-dependent fundamental mass. So I've folded in the field into a definition for the mass of my fundamental particles and rewritten my equations in terms of this. And this is more than suggestive, in fact, that can be elevated to an action principle, where now I have, again, a minimal Lagrangian for my scalar itself, and I have introduced the coupling. The way I've coupled my scalar to my matter sector is by taking the normal special relativity action of point particles and promoted all the masses to functions of phi. And then my couplings in that theory, the particle couplings are obtained by differentiating successively this function of this phi-dependent mass function. And so now I've taken a fifth force model and exhibited it as a model of field-dependent fundamental constants, where the fundamental constants are the masses of the theory. You could try to do the same. You could try to start from the point of view of varying fundamental constants, and so it was a question of interest some 40 years ago whether the fine structure constant had evolved as a function of the cosmological time of the cosmological redshift, and so Bekenstein, as well as others, wrote essentially this model where they promoted the fine structure constant to a function of a field, and introduced the dynamical Lagrangian, and they wrote this model, and you can expand it in the limit of smart coupling. And the idea here is that, well, once the field phi acquires dependence on space and time, it induces a corresponding dependence of space and time of the charge of the electron. And so, for example, if phi z is the cosmological condensate, dark matter condensate that I've invoked on my first of three pathways, this would mean that there would be the electric charge would acquire dependence on the cosmological redshift as the cosmological condensate redshifts itself and redshifts and oscillates. But this is also a fifth force model, because even though I'm coupling to, because I've told you that in order to get a fifth force model, I need a field-dependent mass. Okay, well, the mass of electromagnetic bound states depend on the value of the fundamental charge, right? And if you even think in terms of renormalization, even the mass of, it's kind of an age-old question of renormalization. How does the mass of the electron depend on the value of the fundamental constant? Which comes first? Ultimately, you have to do the renormalization procedure, but ultimately what this says is that most of your masses in the standard model have, say, for example, the nucleons have a QCD contribution and electromagnetic contribution, which depends on E, which depends on phi, therefore M depends on phi, therefore you have a fifth form model of the type I've already mentioned. Feynman diagram corresponding to that is the following. You just attach the scalar to the internal photons of your states. And so basically, this is sort of the recipe for building a Lagrangian in cosmology that has scalars that do interesting thing. You have the gravitational sector, the Einstein-Hilbert action. You've got your dynamical scalar, which both gravitates and responds dynamically to gravity and other forces. And then in the matter sector, you take your favorite matter theory, whether it be the SM or theory of the dark sector. These theories are specified by a set of fundamental constants. You make all those fundamental constants functions of phi, and that will give you, I mean, you can see that in this, written down in this term, really, modulations of fundamental constants and models of fifth forces are really one and the same, although in practice, in terms of equations, things that come about from spatial fluctuations of the field, because forces really come from spatial gradients, then you can think of forces as coming from the fluctuations of the field, and modulations of fundamental constant from coming from the homogeneous part. And so hopefully, once you've written down that Lagrangian, you can sort of easily believe that even though you might want to model build by leveraging only one of those aspects, and sometimes it is possible that one of those aspects sort of bubbles up to the top and becomes the dominates the phenomenology. Clearly, it's everything everywhere all at once. It's all included in the same Lagrangian. So I'll then proceed to give a couple of examples of the consequences of these interplays. So let us consider, for example, a gas of a primary dark matter particle, which we're going to call a key. It's a very simple sector. It just has particles with mass k, so it has one fundamental constant. I promote that fundamental constant to a linear function of phi. As I said, a mass that depends linearly on the field is a good model for Yukawa interaction between your key particles. And I will touch very briefly on this because Diego, I believe, will cover this model more extensively. But what I will say is a consequence you see right away from the background is in terms of the relic abundance of the misaligned scalar condensate. Your Klein-Gordon equation now, which dictated the unfreezing and oscillation of your field, now has a Poisson-like fifth force term, a 4 pi g rho type term. And what that does is it says, well, even if you try to initialize your scalar at zero abundance at the start, say at reheating, as you can see on the plot, the key particle, the cosmic back of key particle, is going to kick your field and effectively give it an effective misalignment angle, such that at late time, it will look as if you had, well, a misaligned condensate, right? And so you had started with a model of fifth forces in a dark sector, but what you ended up with is a mixed dark sector, which has some small abundance of an ultralight component, because presumably the fifth force, if it is to be phenomenologically interesting, is going to be long range. It's going to have the scalar is going to have a light mass in a sense. And so that's one of the unavoidable features of this model is you might think, oh, I'm just going to have Yukawas between my keys, and you will have that. You'll also have an ocean around you of on-shell oscillating condensates, which will modify the Hubble flow, which will modify all sorts of things that need to be taken into account. So this is the evolution of the energy densities. So you can see, so this is focusing on a mass that is heavier than equality. So during radiation domination, the key component, which is here the green line, sources the blue component, which is the phi line, and then at late times, you have three components that behave like matter now, the key, the phi, and the baryons. I think I'll circle back to the hot bath if I have the time later, because I want to switch gears and talk about, move to a different functional form for the dependence of my fundamental constants, namely quadratic dependence on the scalar field. So promoting a mass scale in your theory to, in this case, the mass of the electron, to a quadratic function of a scalar field. You need suppressing the linear part requires sort of moderate model building effort. You can invoke a symmetry, a Z2 symmetry of sort. What is, I don't know if it's nice, but it's certainly a true feature of quadratically coupled theories that they mediate a fifth force that is weaker than the linear theory. But then the fifth force is no longer a Yukawa type force. It's generally a much weaker force. And in the same way, the in-medium dynamics, the dynamics induced by the cosmic bath, will correspond to an in-medium mass term, as opposed to a kick that will give you an initial misalignment. And so these models are perhaps better probed by looking not at their force signatures or at something like an overclosure limit bound, but rather by looking at time variations of fundamental constants that would track the variations of the scalar condensate. And so in this case, we were interested in tracking, in using this as a model for potentially, I believe Colin mentioned it in his talk this morning, there was some interest in looking at whether the mass of the electron could have a different value in the past at early cosmological time. However, remember this condensate oscillates at late times in the late universe after, and if it oscillates too fast, well, you can imagine that's not great, because if the mass of the electron changes, but it changes at a very rapid pace, you can imagine this is hard to monitor. If it changes too slowly, this is also not great, because physics humanity has only been around for so long. And if your scalar is 10 to minus 28 eV, that's about this order 100,000 year. Maybe you can look at the electron for a very long time, and you're not going to change its mass much, just because we were unlucky and the Earth, formed at a time where the field was hitting a minimum or something like that, right? So this is a great opportunity to leverage cosmology. Why is that? Well, first of all, we have probes of the values of standard model fundamental constants in the early universe in the form of BBN and the CMB. And their cosmological redshift works in our favor, because if there exists today a small modulation with time of the size of the standard model constants, going backwards in time, the field will blue shift, if you will, gain amplitude. So this modulation was larger at earlier time, and so potentially easier to detect. And also, if we pick a mass such that the field remained frozen forward in time until sometimes in between recombination and today, then it means that through recombination, the field was cosmologically frozen, which removes the complications associated with an oscillation that is either too fast or too slow. So now we turn our attention to the CMB as a probe of the mass of the electron at early times. So it is true, well, I guess I lied a bit. The CMB is a probe of the mass of the electron at early time, but the CMB by itself is a terrible probe of the mass of the electron at early time. And the reason is, because once you allow the mass of the electron to float in the equations relating to the release and propagation of the CMB, people have identified that the following cosmological parameters, namely the baryon density, cold matter density, and Hubble today, are all degenerate with the mass of the electron, right? And so what we show in this plot is we've generated, so the direction of degeneracy is here on the left, and we've generated CMB power spectra where we've varied the mass of the electron by more than 15% on either direction, and we've adjusted by hand the other cosmological parameters to scale in according to this way. And what this shows is that the CMB TT and polarization power spectra are essentially blind to this change. They're degenerate. So this is, I was going to de-emphasize the role of the Hubble tension, but since it was mentioned this morning, this is the observation of this degeneracy or a version of it was invoked as potentially a way to alleviate the Hubble tension. The idea was that, well, it looks like if I allow ME to be bigger at early times, maybe I can also allow Hubble not to be bigger at early times, and maybe there's some thing I can do there relative to the Hubble tension. It turns out to not work all that great, but still, and for reasons that I will talk about. Okay, so that is just the CMB by itself. But certainly a reason it doesn't work just as a minimal vanilla model is that because the CMB is not only observable, you also have observables that probe the redshift of matter lambda equality, and this degeneracy direction does not leave the redshift of matter lambda equality fixed. So yes, so the degeneracy is lifted by low Z data set, BAO, uncalibrated supernovae. But all I've said so far regarding the CMB and fundamental constant does not account for any microphysics. It does not account for the dynamical field, the dynamics of the field that are in principle responsible for driving the change in the fundamental constants. In particular, as I said, this is a light scalar that starts oscillating well into matter domination, and so it will add hyperlight matter density at late times. Okay, well, maybe if it adds significant amount of matter at late times, it could preserve the degeneracy direction, right, by allowing us to give an additional knob to fix the redshift of matter lambda equality. And okay, maybe that salvages our path towards alleviating the Hubble tension, but careful though, you're adding matter at late time, but you're adding hyperlight matter at late time, which we know the CMB doesn't like because it suppresses the growth of structures. So your ability to do that will be limited. Okay, so now just in terms of numbers, how does the shift of the electron mass relate to the field parameter today? The field today can be characterized by its present-day abundance relative to dark matter and its coupling to matter. For a very light field, the initial misalignment angle is in direct proportion and directly related to its relative abundance to dark matter, its abundance relative to dark matter today, which means that the shift of the electron mass at early times relative to today is exactly the product of the relative abundance today times the coupling constant. And this last equation is, I think, a nice instantiation of the interplay I was telling you before. It's a product of a particle physics term and a gravitational term. So you could say, well, maybe I'm gonna, maybe I have fifth force experiments that constrain the particle physics really well, so I'm going to give it a tiny coupling, and if I want, assuming, say, I detect a deviation from the mass of the electron, I'm going to achieve that by giving a tiny coupling and by boosting the relative abundance. Okay, well, that's fine, but as I said, now you're introducing large gravitational effects, and you could say the other way around. Maybe I want to have benign gravitational effects and tune up my coupling, but now you're coupling more to the bath of the electron bath of the universe, which means you'll generate a very large effective mass, and now the dynamics of your field are going to be nothing like what you imagined, right? And so at the end of the day, to resolve, there are different phenomenon here pulling in different directions, and which one wins out? Ultimately, one needs to simply perform a parameter inference on joint cosmological data sets that include your lambda CDM model plus ME plus phi, or equivalently lambda CDM plus coupling plus phi. On the left, you see what is our bounds from CMB SDSS for the product D coupling times abundance, which, as I said, is pretty much you can think of as a bound on the shift of the mass of the electron early times relative to today. You can see that this is constrained at the percent level by the joint cosmological observations. And then on the right-hand panel, you're trying to unpack this and see if you can get individual 2D posterior on the abundance and coupling independently. And what ultimately I think is revealing there is that, well, like as you can see, the relative abundance is bounded, is excluded to be any more than order 10 to the minus 2, which is pretty much the same bound that was obtained in just an analysis of just the CMB, right? So there might have been a hope that the CMB bounds on ultralight components somehow get relaxed if you free up the mass of the electron as a free parameter, as a floating parameter, and that turns out to be not to be the case. And in fact, that limits your ability to, well, exploit this degeneracy I was telling you about, because it tells you, no, in fact, you cannot add a large amount of dark matter at least times to come and stabilize the redshift of matter lambda equality. And then it also showcases that Planck is what I was telling you. Planck itself is not great at putting bounds on anything, but Planck plus BAO is a much more stringent bound. And then we don't really plot that, but if you were to go at the very small value of f, you would eventually hit your red region would eventually hit regions of the coupling, of large couplings, where you wouldn't necessarily be excluded, but the analysis would have limited value because now your field would be oscillating during recombination. And so you would not be working with the model you had in mind. So that's about my time. So yes, scalars are associated with at least 3 kinds of physics. They're dark matter candidates. They can be fifth force mediators. They can be drivers of variations in fundamental constants. And the interplay between these three physics generally must be taken into account if we are to consistently probe, constrain, leverage the parameter space of cosmological scalars coupled to matters. Thank you.
Do we have questions for Olivier?
Anyone wants to know about the hot bath? Okay. Okay. Go ahead. Yes.
Good. Two questions, one about models and one about observations. In terms of models, so you're dealing with hyperlight scalars. How are you preserving the lightness of the scalar?
Yeah, absolutely. So certainly for the quadratically, the quadratically dependent mass of the electron, that is well into unnatural. The constraints are well into unnatural parameter space, and you sort of have to come to peace with that, I suppose. In terms of other model building aspects, the model I gave you for potentially a fifth force in the dark sector. In the dark sector, you have the freedom, I guess, of not knowing what the key particle is. So if you make it a scalar, then your operator is key squared is three scalars, which is a super renormalizable operator. So that salvages that helps keep the scalar radiatively stable. Other games people try to play with these scalars is if you make all the coupling functions exponential, then you can exhibit that at least at the classical level, a mass term for the scalar is a spurion for breaks a scaling symmetry. There's a scaling symmetry in the massless case. And that also helps. Ratazzi had a paper on how that helps keep dilatons light. So yeah, so from the bottom up, these coupling functions are kind of arbitrary, but yeah, considerations like keeping the scalar light radiatively stable might further constrain them. Sorry, yeah.
And the second follow-up quickly, on the constraint plots, where would like atomic clocks pop in at all?
Oh, good. Very, very high, because atomic clocks suffer from being experiments that are short-lived today. And so once you factor in the uncertainty of maybe the field, but once you factor in your uncertainty about the phase shift of the field, okay, maybe in order to clarify, in the case of a quadratic scalar, the signal depends on the actual value of the cosmological dark matter at Earth, right? And so if it oscillates and you factor in that uncertainty, you end up penalizing your bounds quite a bit. So for the hyperlight parameter space, for these very, very light fields, the dominant bounds are CMB, BBN is also competitive, quasars, because you have a number of them so that you can poke the field at different times and reduce the likeliness of being at a node. But clocks are way over there for the but this is because it's a quadratic coupling. If this were linear, they would be much stronger.
Any other questions?
Yeah. What is this quasar bound?
Oh, it's from the observation of basically the quasar absorption. So it's the observation of quasar absorption lines. Basically, if you any atomic spectra depends on ME and alpha, and so the quasar, when it absorbed the line, absorbed at the redshift of absorption, right? And so if there's a difference between the value of alpha or ME at that time relative to today, then the spectrum will be shifted or distorted, right? Because it changes just atomic physics at that place, at that time. So that gives you a constraint on how different the atomic constants are today relative to when the absorption took place. Yes? No, but I hear you, so.
Okay. I have a question about the fifth forces. So with a quadratically coupled model, I would expect, as you said, very weak fifth forces in the case of no VEV. But if you're also using, I assume that the scalar VEV is also changing the electron mass.
Sorry, what?
So I assume that the scalar has a vacuum expectation value, which is changing the electron mass for you.
The scalar as a, well, sorry, it's oscillating around its zero. So I'm not sure what you call by
I
vacuum
see. Okay, so
expectation
it's not tracking a.
No,
it's just oscillating.
it's not.
Okay, I see.
And that relies good because because both the coupling. So the total potential of the scalar is really it's vacuum potential. So it's mass term, it's parabolic mass term, and the matter potential. But the fact that we've stated once we pick all of them to be quadratic, this is a non-trivial statement. This is essentially saying that all these potentials are aligned, and so that the zero of the field is at the zero of the mass, the same zero as the mass.
I would expect a non-zero fifth force as soon as the scalar is not
Good. So that can be understood by the size of the force being modulated by the condensate around it, right? And in this case, that's true. There is a cosmological condensate, but again, it's oscillating. So if you factor in the fact that there's an uncertainty regarding to the phase, the fifth force constraints are also lifted quite a bit.